Welcome to a new test and teardown video. This time it's another spectrum analyzer. This one is from Anritsu and it's a model MS610B. It only goes to 2 gigahertz, but it's actually quite nice. Modern kind of size and all that. And it should actually power up and more or less work, but I heard it should have some sort of bugs and problems. I got this, I don't know, a year ago. Traded some other equipment, and then I got this one. So finally I got time to play with it. So let's power it up and see what happens. And we got a little bit of, oh, we even got a picture. So this is the, okay, that is weird. So we got a little zoom window here and we got intensity. And that is the gain. Well, so here is my center frequency, right? Okay, here we go. It is not responding to that. Let me input 100 megahertz. Oh, look at that. Let me turn it off. So that is 100 megahertz. That line there. Now it's on. So, okay, it's not responding to anything. Resolution. Okay, so those switches here, span, no response, and that is the attenuator. What am I doing wrong here? Okay, span and then data. I'm just feeling completely lost here. Oh. So after massaging the switches here a lot of times, I finally get a little bit response. So this is the frequency span, and by hitting that one and putting it into 0.2 gigahertz of span, that means this should be 0.2, right? And then this is of course 0 hertz. And then if I turn off my 100 megahertz test, that is in the center, then it works. The center frequency here, I mean this readout, I don't understand exactly how that works, because it moves it like this, but it's definitely not accurate. As you see here, if this is truly the span is right, because I can see that works. If I change my input frequency from 100 megahertz to 150, see, it's right there, and then that is 200. So that is the span. So span works, but center frequency here does not work. So start frequency, aha. So that is weird. I think I'll go back to 100 megahertz and then play with start frequency. Start frequency should be 0. Okay, so that works. Aha, so I dial this in and then I can hit my center frequency. No, I cannot. I mean, this is not working. Frequency 0 adjust, so there is something here. Maybe I need to adjust this. Maybe that is, no, this is not the right one. I'll have to play a little bit with what is going on here, because, okay, so that center frequency is 100. And then, now I have fixed it. So what if I change my frequency to 200 megahertz and then I dial my center frequency into 200? Haha, now it works. So all I can see, we have a all the problem is only related to the switches here. They are not working, so I need to disassemble it and clean the switches and see if I can get that working. Video filter, oh yes, that works. Or off. That is really a weird filter. So this is a 10 kilohertz filter. How about I change the span? Yeah. Because now, haha, you see, I really need to push it a lot. So that is 5 megahertz span, and my center here is now 200, exactly as I give it. And then we can play with the filters. Well, I mean, it really works. That is so cool. Yet this unit is already driving me nuts. I don't know. Look how many different type of screws I'm already playing around with, and I'm not even in. So it's from the bottom, the back, and the sides. See, all sorts of different screws. For every little detail, we're using different screws. How nice. So now I took away the front plate, and that is actually a little bit difficult to do. If you see here, we got those thin pieces of metal here, this little steel thing, and those actually hold the front plate, and they are, as you can see here, there's some screws that goes through and presses this at the correct position. And let me show you the other ones. They look a little bit like this. They are longer here at the top, but at the bottom they look like this. So it holds the front plate like this, right? See? And so there's a groove here, so that means if you loosen the screws, you don't even need to take them all the way out, but just loosen them, then they will come up when you pull the front plate up. And then down here in those holes you have some acrylic pieces with text on them, and you see light can shine through and show the text, and they will fit. Megahertz fits here, of course, right? And so forth. So the problem with all the switches, that is definitely only the switches and not the electronics, because what I've done is I powered this up, and then I took my little tweezers and touched the sides of the contact, and then I proved that I get perfect response on this is the data up down buttons, and those are of course the most used buttons, and they're just completely useless no matter how much I push. And then there's this little plunger, and if you see here, it's held back by those two little locking mechanisms here, and I kind of break it more or less by using a screwdriver. So I'm going to invent a little pull out tool by some very thin metal that I can stick in, and then I should be able to pull up the plungers without breaking everything. I can heat this up a little bit and bend it in, and then it should work again. And then we got, here is the contact, but it's only touching 2 points, because you can see there's like 2 points down here. So if I take this up and just rotate it halfway, or I think just put it down again and then clean this up a little bit, then I'm probably going to get good contact. So this is what I'm going to try now with those two, and see that it should be able to work again. You gotta see this. Of course I only cleaned these. So when I changed from frequency to attenuator, see, those are a little bit lame, but they do work. But now I am in frequency. See? I get a very, very good and fast response now. If I go to the attenuator. Click, click. Ha, man. So I fixed it. Ha, what a lucky day. So after I fixed the data up down buttons, and that's probably the most used buttons, it's actually good enough for my use, because the other two buttons that is a little bit annoying, that is frequency span and input attenuator. And of course they are very, very important, but they kind of work. I mean, it just takes a half a second for a response, so I think I'm just gonna live with that. And that is because there's an LED in here and it's difficult to remove, and I'm probably gonna break the LED or something like that. So I just live with the a little bit slow response, but there is definitely a response, and now data is super good. So I'm actually quite happy about it. I'm gonna clean it up nice and shiny and assemble it again, and then I'm gonna start to play a little bit with it. So this is the input module, or the RF board. In here we got two filters for 2.5 gigahertz, and this is the jig oscillator that is running from 2.5 to 4.5 gigahertz. And the first IF is at 2.5 gigahertz, so that is what those filters are for. One is a bandpass filter for 2.5 gigahertz, and the other one is a low pass filter for 0 to 2 gigahertz input. And of course I'm not going to open this because I don't want to screw up the alignment of the filters, and it's just a cavity filters, and they're adjusted from the other side. And in here we actually got a little bit of alignments from the top. Let's look a little bit at the block diagram of this entire unit. In the upper left we got RF input, and then there is this the first mixer. To the left of the first mixer is this low pass filter I talked about. It is from 0 to 2 gigahertz, and that is of course the frequency range of this spectrum analyzer. And under the mixer is of course the jig oscillator that runs from 2.5 to 4.5 gigahertz. And to the right of the mixer we have of course an amplifier and a band pass filter, a very narrow 2.5214 gigahertz band pass filter, and that is the first IF. And then there is a fixed 2.5 gigahertz oscillator, that is of course the second local oscillator, and the output of that mixing generates the 21.4 megahertz second IF. And then there's of course new filters and new gain blocks, and then we mix it down by a 24.9 megahertz oscillator. That's called the third oscillator. And then we go into the final IF that is 3.5 megahertz. I will show this IF block later, and then you'll see how this is made. It is actually a very, very big PCB in the bottom of the unit. And then the rest is just quite boring stuff that just sweeps the DC voltages that controls the jig oscillator, and drive a CRT and stuff like that. It's not super relevant for understanding how this unit works. I wanted to see if it's possible to go down here and see the CPU card and the IF filter card. We also got some power supply stuff in here. I think you can see the power inductors and all that kind of stuff down there. Mains transformer is far away from the CRT, not completely far away, but that's just the way it is because we need the full depth input board or this input module. And the fun thing is this aluminium frame with all the filters and all that kind of stuff, that is actually the same one used in many other Anritsu spectrum analyzers. It's just a little bit different with the filters and the rest of the stuff, but mechanically it's the same bracket. So that's interesting. And that will be the IEEE interface, and that goes of course to the main CPU card. And this one is running with a 80C85 CPU down here. And that is some stuff for the CRT. And that is of course trace rotation. And down here we got the CRT drive. And here's the CRT drive with the 2 deflection amplifiers. So here is the 0, or the position of the horizontal and vertical. And this is the anode. I don't know if you can see this, but here is the anode. And that will be the Doppler, and that will be the transformer for the high voltage stuff. There's not a lot really. It's not a super big CRT, and it's scanned at a low frequency. So that is why we really don't need a lot of high voltage. So now we are at the bottom, and that is of course just a shield for the back panel connectors and stuff like that. I actually wanted to inspect that as well. So let's have a look. So here in the bottom, that is the IF section. And I've been inspecting all the capacitors as good as I can, because my other Anritsu really suffered from dead capacitors all over the place. But this one is super duper good and tip top. All the capacitors are nice and fine. I don't see any leaks at all anywhere, so that is great. So like I said, this is the IF section, and here is our 21.4 megahertz input, and then it's mixed with 24.9, and then it becomes 3.5 megahertz, and that is the last stage. So all this is IF section and resolution bandwidth by relays, all the different bandwidths and amplifiers for all that kind of stuff, and filters for that. And then that is the last amplifier before it goes to the log amps. And of course there is a relay to switch between linear and log mode, and that will be the detector that drives more or less the deflection for the CRT. So let's look a little bit on the CPU section. I hope I can get all those connectors back in. I took a lot of close-up pictures, and also wrote down some of the numbers that's written on the PCBs. And the fun thing is, more or less all of them is wrong. What the cable is called and what is the connector called where they made, that is wrong on more or less all of them. So what the heck is going on here? I don't know. That is that is why it really pays off to pay attention to this kind of thing. So here is the CPU and interface controlling. It's also doing the scan and all that kind of stuff. It's actually a quite beautiful design, and to avoid contacts between the two boards, they're using those flat kind of cables that you solder directly into each board, and that is a very good idea to avoid loose contacts. Definitely something I like. Well, I would like to open this and show you guys what's going on in here. I also want to clean the contacts down here. They look quite dirty. See, that is the scan, and the other one is the CPU card. So let's have a little look at the scan card. So that's full of analog and digital sample, hold, and analog switches and op amps and stuff. And then we got the CPU card with the 80C85 CPU and the EEPROM for the program, RAM. I think that is a timer, and that is a parallel input output. We got analog parts, and look at that. There's a little prototype area here where you can put in a new IC, power it up, and wire wrap some wires to do some sort of a debug or development on this board. And I've actually seen this quite a lot on very old designs, to just use this unused space for future developments or test of future features and stuff like that. Pretty cool. Yeah, we are running at 4 megahertz. And all the parts, we got date codes 86. I don't know if you can see that, but more or less all the date codes, that is 86. So I believe my spectrum analyzer is from 1986. So I pulled out the power supply, and it's not even connected. At the bottom here, there's only those 2 cables coming out of this thing. And the fun thing about this power supply is it consists of 3 switch mode power supplies and also 3 linear power supplies. And it's actually really, really beautiful designed. Hey, look at that. What kind of lock is that? Have you seen what that is? This thing, I think I need to pull this out. But that thing is the timer. The timer is a 5,000 hour timer. And that will show me how many hours this unit was actually powered up in total. And those are really, really fascinating. So I think I will try and open this a little bit more maybe. So here's the 5,000 hour timer. It actually consists of some mercury inside a glass tube, and then there's a tiny little gap, and I think maybe there's a gas or some kind of stuff in that gap, and when there is a voltage difference, then the molecules or something like that from the mercury actually change position from one end to the other and just moves slowly. And this one measures 2.3 kilo ohms, but I can't see this gap anywhere, not here in the visible area. And of course it should be, if this one was brand new, it should have been around 0, right? And then this gap moves to the right. And if I look all the way in here in the end, it looks like there's a little bit of something at the very end. So that means this one ran all the way to the end and just stayed there forever. So I can't tell you how many hours this unit has been running. That is bad. And the fun thing is you can reverse these. If you flip the direction, it's gonna move back. So that is also a lot of fun. Maybe I should just put this on my on my table somewhere and put in a DC voltage and then just come back 5,000 hours later. That could be cool. So yeah, and those are the small nasty capacitors I normally expect would leak. It's not always the largest, but that kind of size is a classic problem in Anritsu. But in this one, they all look absolutely nice and shiny. And also, if you look at all the PCBs, they're really nice and clean. And of course, this is because this unit is not using a fan. So that is why it's really nice and clean. So let's try and play a little bit with this unit now. I'm completely done cleaning up and assembling and everything. So this is just a power up. I didn't touch any buttons at all. So at first power up, it always starts in full span, and then it shows here it is in span, and this one is lit. So that means whatever I'm doing here on data, it should be span, right? Because this one is lit and this one is lit. So that means if I click, see? So that's 1 gigahertz. Oh, it was full, right? 1 gigahertz, 500 megahertz is now my span. 200 megahertz. Okay, fantastic. So if 200 megahertz is my span and my center frequency is 246, I want my center frequency to be 100. See? What happens now is my 0 is now shown here. So this is actually the jig oscillator that is shown, that goes straight through the mixer and straight through the IF filters and all that kind of stuff. This is exactly what you see here, is the injection, the frequency injection. So if I move my center a little bit down, then of course I'm not seeing frequencies that is under 0. That is of course not possible. What I see below is actually the mirror. So everything that happens on the positive side also happens on the negative side. And let me demonstrate this by inputting, let's go to 10 megahertz and then enable. So let me make it a little bit more bright. So here is positive 10 megahertz, but it's also a 10 megahertz mirror. So what happens if I move my 10 megahertz? Let's do that by doing like 20 megahertz, see? I think it's easier if I do like this, 20, 30, 40, 50, right? So that is my mirror, it's just the same. So if I go all the way to 100, it's of course not possible to go that far, I guess. Yeah, okay, you could actually do that. But anyway, let's get back to measuring my 100. So here's my 100. It's supposed to be exactly in the middle, and it is a little bit to the left, as you see. And here's what you do. Since everything here is of course analog, and it's just warming up, so you need to wait a little bit until it's done warming up, and then everything will drift a little bit. The voltages that controls the jig will of course change a little bit, and then my 100 will of course be in the middle. So you need to wait a little bit before you do calibrations, and so I'll have to do that. And if we go back to marker level, see, here is my power, my minus 30 dBm. That is my input level. And it's only measuring in the middle here. So if I tune, see, the signal goes away, right? So this is my noise floor, and here is in the middle, here's my signal. So the idea is you fine tune to the highest level, and then you measure the frequency. You can of course change the resolution bandwidth, and you can zoom in if you want to do that. So here's my span. Let's go. See? I needed to push this a little bit extra. And then that was my attenuator. This is span. Okay, so 0.1, 50 megahertz, 20 megahertz. See, I can just zoom in. So here's my 5, 2, 1 megahertz. .2 megahertz, okay. Then it goes super critical on the big one. Then I go to the fine. See, then I can go and find my 100 megahertz, and then I can of course go into resolution bandwidth, Then I can change my filters to make them wider or smaller. I can also change here my filter here as well. And this way I can get a really nice signal. Oops, I'm a little bit off again. And then I trim it in. How lovely. So, all in all, I really think my unit here really works. Oh yeah, by the way, oops, it's on cal. Yes, that is how it works. To be able to calibrate the level correctly. So here it's 28 dB. What you do is it's actually analog. So you just dial this knob until you have the correct level. And of course you need to know, let me dial this. You need to know the level of your signal generator. No, see, it's drifting a little bit because I'm really zooming in now. Maybe we should test for its calibration output and see if that is accurate. By the way, the calibration oscillator in this unit is just a free running oscillator. It's not locked to anything at all. It's just controlled by a positive 12 volt supply. And so of course, if that 12 volt supply is accurate, yeah, then I should have my output. Yeah, I'll try and play with that. So here we're actually using the spectrum analyzer to measure its own 50 megahertz calibration output. And of course I had to dial this up a little bit because it is a little bit on the low side. Also, I got a little bit of loss in my cable. And here's the funny thing is, this is 100 megahertz, this is 50. Look at that, the harmonics. So the second harmonic is only 10 dB low because I got 10 dB per division. You can see that here. So 10 dB per division, yeah. And we could actually zoom up a little bit. Let's look at some more. Now my 0 is here, right? Ooh, yo, 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 yo. And then, of course, I need to remove my signal and dial my 0 down to 0. So now my center is 250 and my span is 500. See? That is a lot of harmonics, exactly as I want, because I actually want this to be able to calibrate for correct frequency. And since this is 50 megahertz, that means it should be 50 megahertz per division here. And all I have to do now is stick in my little adjustment for horizontal, the width, and then make the beam a little bit, the picture a little bit wider, so I can actually calibrate this readout here so it's accurate. And that is definitely how you do this, because it's analog. I really don't want to say a lot more about this really, really cool spectrum analyzer. I'm just super happy about it. And thank you very much for watching, and bye bye.